The objective is strictly defined: return a heavy bomber to airworthy condition under the United Kingdom Civil Aviation Authority permit process for ex-military aircraft. The target airframe is Avro Lancaster B7NX611 Just Jane. Constructed in April 1945, the aircraft missed combat operations during the Second World War. By 1983, it was acquired to serve as a living memorial at an aviation heritage center. Now the engineering team faces an operational constraint that completely overrides the easiest form of aircraft overhaul methodology. The estimated capital required to restore this heavy bomber to flight status is £4 million. To finance this exact objective, the Heritage Center depends on a continuous stream of public funding, including museum admission, donations, and revenue-generating taxi rides. The aircraft must remain mechanically complete and capable of conducting those taxi rides through the operating season, making the conventional overhaul model procedurally impossible. Normally, a large restoration would move into a dedicated hangar, separate the major sections, strip and inspect them, and rebuild the airframe on a continuous engineering timeline. The restoration must preserve enough structural integrity for summer taxi testing while planning the replacement of the same primary components. The physical restoration must be executed piece by piece. Deep maintenance and structural teardown operations are strictly confined to a precise 6-month winter interval. When the summer revenue season concludes, the aircraft is immediately positioned inside the maintenance hangar and partially dismantled for targeted inspection. Before the subsequent summer season begins, the deep structural work must be halted. The heavy airframe must be meticulously reassembled, inspected for dynamic ground operations, and certified mechanically sound to carry passengers during high-power taxi runs. This rigid operational cycle forces the engineering team to plan heavy structural interventions in highly segmented, unyielding phases. A missed deadline would not merely delay the work, it would remove a critical funding season from the restoration plan. The procedural problem scales directly with the complexity of the historical aircraft. That limit becomes critical when a primary load-bearing component needs more than one continuous winter cycle. The physical time required to drill out structural fasteners, inspect inner metal skin sections, and manufacture aerospace-grade replacement parts consistently exceeds the available winter downtime. The airframe cannot be left in unassembled pieces during the primary funding season. The technical path forward still requires physical access to hidden load-bearing structures that must remain stable for taxi operations. The question becomes how engineers can open that structure without permanently grounding the aircraft. The structural limit of an 80-year-old aircraft is rarely determined by continuous flight fatigue alone. The most aggressive degradation occurs chemically at a microscopic level. For a historic heavy bomber, the governing threat is dissimilar metal galvanic corrosion. This specific airframe did not spend its entire operational life in a temperate climate. Following the Second World War, the aircraft was transferred to the French Naval Air Arm. Under the designation WU-15, it operated as a maritime patrol asset in the Pacific Ocean. The operational environment forced the heavy bomber through highly corrosive salt-rich atmospheres for extended durations. Later repatriation required flying 12,000 miles across global weather zones to return to the United Kingdom. These environmental cycles pushed aggressive saline moisture deep into the internal structure of the wings and fuselage. During the original 1940s manufacturing process, engineers combined multiple metal types to achieve specific load-bearing requirements. Aluminum alloy formed much of the primary skin and light internal structure, while steel fittings, ribs, brackets, fasteners, and reinforcement pieces appeared where higher strength or local stiffness was required. At these contact points, salt moisture becomes an electrolyte, leaving the steel hardware relatively stable while the adjacent aluminum structure degrades. This electrochemical reaction directly eats away the aluminum mating surfaces. The process fundamentally compromises the precise load transfer capability between the inner steel framework and the exterior aluminum skin. The primary forensic hazard of this chemical process is its physical location. Corrosion can appear wherever coatings fail and moisture is retained, but the most dangerous pockets in a restoration like this are often hidden inside overlapping seams, fastener lines, and internal mating faces where salt moisture can remain trapped. Severe corrosion can therefore remain structurally invisible from an external visual survey. Assessors examining the smooth outer aluminum skin may not see the material loss occurring on the hidden inner mating faces. The required engineering response is therefore conservative. Every original interface where steel hardware, fasteners, or fittings meet aluminum structure must be treated as suspect until it is exposed, inspected, and proven acceptable. The original wartime assembly used thousands of tightly spaced solid rivets and clamped seams, creating exactly the kind of closed interfaces where Pacific-era contamination could persist beyond external inspection. Because the Heritage Center must maintain the airframe for immediate summer taxi operations, the engineering team faces a severe diagnostic limitation. They cannot simply cut large exploratory access holes into the wings to map the extent of the decay. The aircraft must retain its physical rigidity. Standard non-destructive testing methods face significant boundaries when scanning complex, overlapping, multi-material joints. NDT can reveal many defects, but layered skins, fasteners, sealants, fittings, and tight contact surfaces can still leave uncertainty about the exact condition of hidden mating faces. In those areas, the final proof often comes only when the joint is physically open. The engineering team is forced to adopt a conservative structural baseline for every suspect interface. The exact loss of material thickness directly correlates to a loss of mechanical margin. In a low-stress area, damage may be assessed, blended, repaired, or accepted under approved data. In a highly stressed spar web, attachment radius, or primary skin panel, even modest material loss can invalidate the original safety margin unless it is formally assessed and approved. Eliminating the threat requires more than surface-level corrosion inhibitors. Accessible areas can be protected with sprays and coatings, but suspect closed interfaces require full remediation. Remove corrosion products, repair or replace damaged material, and reestablish a sealed structural boundary. If the deepest structural decay is physically trapped beneath tightly overlapping skins, how can inspectors verify the structural limits? The mechanical threshold between ground operations and actual flight creates an absolute engineering divide. An aircraft capable of running 4 Rolls-Royce Merlin engines simultaneously can still be mathematically unsafe to leave the runway. The Heritage Center operates the heavy bomber to a strictly defined taxi standard. This operational baseline requires the airframe to safely absorb continuous high-frequency engine vibration, multi-directional propeller thrust, and the localized shock loads of rolling a massive vehicle across uneven concrete. During ground operations, the main vertical weight path still runs through the center section, engine bays, and landing gear, but the loading is not purely compressive or two-dimensional. Taxiing adds braking loads, steering loads, vibration, propeller thrust, inertia, and local bending through the attachment points. The outer wings and rear fuselage are not asked to carry full aerodynamic lift, but they still have to remain aligned, attached, and dynamically stable as the whole machine moves across concrete. Airworthy flight certification requires transition into a completely different physical and regulatory reality. The moment the landing gear leaves the runway, the primary load path abruptly inverts. The wings must instantly generate and distribute enough aerodynamic lift to suspend the entire weight of the loaded fuselage, all 4 engines, and the internal fuel mass in midair. This dynamic environment subjects the airframe to massive upward bending forces, continuous torsional twisting, and alternating positive and negative vertical acceleration loads encountered during standard atmospheric turbulence. A civil aviation authority will require mathematically verified load tolerances, not a history of successful ground runs. Because the fundamental condition of the 80-year-old internal metal cannot be guaranteed, the remaining life of original structure must be supported by inspection evidence, records, analysis, approved data, and regulatory oversight. Where that proof chain is weak, the safer route is not to test the historic wing until it fails. It is to remove uncertainty by replacing the fatigue-critical structure with newly manufactured, fully documented components. The operational mandate specifically targets the wing spar booms and the tailplane spar booms. These components are the primary load-carrying members inside the wing and tailplane attachments. For a modern return-to-flight case, the original 1940s spar booms cannot simply be cleaned, patched, or chemically treated into a fully documented fatigue baseline. To legally and safely return the bomber to the sky, these central load-bearing components must be completely extracted and replaced with newly manufactured aerospace-grade spar booms. The strategy shifts the proof chain away from questionable original metal and toward a documented zero-hour fatigue baseline, supported by certified modern manufacturing data for the highest stress areas of the machine. Replacing the main longitudinal spine of a wing introduces a severe physical consequence. The spar boom is the exact component that defines the geometric shape and overall rigidity of the wing assembly. Removing it effectively disconnects the lift-generating structure from the rest of the airframe. The surrounding original ribs, stringers, and outer skin panels immediately lose their central structural anchor. With total structural replacement confirmed, the next problem is geometric control. The answer is to transfer the wing into a controlled support system before the primary longitudinal spar boom is removed. Built around the aircraft's required geometry and reference points, the steel jig holds the wing on fixed external datums so internal members can be removed, repaired, and replaced in controlled stages without losing alignment. Once the wing is stabilized in the steel jig and the primary spar is pulled out, the engineers confront a highly detailed secondary teardown phase. The interior of the aluminum skin is lined with long metal stringers that run parallel to the main spar, providing essential stiffness to the outer panels. These stringers are secured to the structural ribs using hundreds of individual metal attachment brackets known as cleats. It is exactly within these overlapping metal boundaries that the hidden corrosion resides. The engineering procedure is intensely manual, but it remains controlled by approved maintenance practice rather than improvisation. In the wing, brackets, cleats, and riveted joints that block inspection are opened in sequence. Original fasteners are removed with care, the surrounding holes and skins are protected, and each separated joint is recorded before the parts are cleaned, repaired, replaced, or reassembled. Removing the cleat breaks the structural trap. Once the bare metal is verified clean and structurally sound, the area is treated with modern aerospace sealants, and a brand new cleat is precisely aligned over the original rivet holes and secured with modern aerospace fasteners. This meticulous extraction procedure must be repeated across large areas of the port wing, turning a single cleat repair into a vast program of specialist labor. Because the wing must remain locked into a controlled jig through this sequence, the physical teardown cannot be paused or reversed quickly. For the wing rotation plan as a whole, the work stretches across several years, allowing each native wing to move through a full 12-month rebuild without the damaging stop and start cycle. The only way to keep that rebuild moving is to separate the long-term structural work from the aircraft's summer operating role. To solve the timeline paradox, the engineering management team selects a highly unconventional logistical pivot, a donor airframe rotation strategy. Instead of accelerating the deep structural overhaul, the team bypasses the seasonal boundary through component substitution, preventing the main aircraft from missing a summer revenue cycle. The strategy requires locating compatible structural sections from other surviving preserved Lancasters. The Heritage Center works with the South Yorkshire Air Museum on the rear fuselage of Lancaster KB976. It also develops an international agreement with Les Ailes Anciennes at Le Bourget to borrow the wings of the French preserved Lancaster NX-664, beginning with the port wing. These borrowed components are not being prepared as certified flight structures for NX-611. The KB976 rear fuselage is restored to taxiing condition under the arrangement with the South Yorkshire Air Museum, while the NX-664 wing is restored to a taxiing standard before it is used as a temporary substitute. The engineering team evaluates these proxy sections for ground operation rather than flight condition. That still demands attachment integrity, alignment, vibration resistance, control continuity, braking loads, steering loads, and the repeated shock of ground movement. But it does not require the donor parts to prove the full aerodynamic lift, bending, and fatigue margins needed for airworthy flight. During a designated winter maintenance interval, the native port wing and the native rear fuselage of NX-611 are detached and moved into the long-term stabilization frames. In their place, the proxy components from KB976 and NX-664 are physically bolted onto the main center section. Mating heavy structures from 3 different historical bombers is a highly demanding procedural task. Each original airframe was built with wartime production tolerances, and even aircraft from the same broad family can carry small differences in fittings, alignment, and routing. The bolting flanges, spar attachment points, and control cable pathways must therefore be carefully checked before the proxy wing is accepted on the airframe. The engineers must ensure the heavy attachment hardware passes through the joint without forcing the metal into a bind. Forcing a mismatched joint would introduce unwanted stress into the framework before the aircraft ever moves. This direct substitution removes the timeline pressure from the primary structural rebuild. The main aircraft remains complete for summer ground operations, while the native wing and fuselage stay undisturbed inside their steel jigs for the multi-year extraction and rebuild process. Buying this extensive time buffer is a strict operational requirement because of the global supply chain. Procuring the new primary structural spine for the native wing introduces a severe logistics barrier around specialist extrusion manufacture. The engineering team cannot patch the original structural backbone into a new documented baseline. They must source newly made spar boom extrusions to the correct specification from specialized manufacturers in the United States. Once manufactured and verified, these long metallic elements must cross the Atlantic Ocean and arrive at a British hangar without damage. Their handling is not casual freight work. The extrusions must be protected from moisture, contamination, and bending loads while they wait for machining and installation. Even before they become finished spar booms, the raw profiles have to be stored and supported as precision structural material. If the main aircraft had been grounded while waiting for the 1-ton crates to arrive, the financial structure of the restoration would have failed. The donor parts shield the project from those external supply chain delays, allowing the proxy wing to carry the aircraft on the concrete while the new aluminum extrusions are manufactured, shipped, and prepared for installation. When the proxy components are finally removed, what shape will the fully restored native airframe take? The final configuration state of the heavy bomber is governed by the deadline to return the borrowed proxy components. Once the original native sections have been rebuilt with documented fatigue, critical components, and accepted into the return-to-flight approval path, the structural substitution must be reversed. The engineering management team must return the borrowed parts to their respective museums and remount the heavily restored original wings and native fuselage to the main center section. The long-term program remains anchored to the historical identity of Just Jane, not the creation of a composite aircraft from surviving salvage. At that moment, the aircraft sheds its hybrid ground testing configuration and becomes a uniform historic artifact once again. The procedural execution of this final swap requires extreme engineering discipline. The same strict tolerance checks utilized to mount the donor parts must be repeated in reverse, as the newly certified native wing is aligned with the original fuselage attachment hubs. Because the native wing has been rebuilt with brand new 30-foot aluminum extrusions and thousands of seated structural rivets, the team must monitor the massive steel pins as they slide through the joint blocks and verify that the new load-bearing spine does not introduce unexpected tension or shear stress into the 80-year-old center section. Reconnecting the main structural assemblies triggers an entirely new phase of mechanical verification. Every flight control surface, from the heavy ailerons out on the wingtips to the large tailplane elevators, must be re-rigged and calibrated. The mechanical control cables running from the cockpit through the restored fuselage require exact tensioning, so the aerodynamic inputs remain balanced. The 4 power plants then move into a structured test program: progressive engine runs, low-speed taxi checks, high-speed taxi trials, inspections, and formal approvals before the aircraft is allowed to separate from the runway. These stages prove that the newly assembled structure can tolerate vibration, thrust, braking, and ground movement before the program advances into initial test flights focused on controllability, handling, engine response, vibration, and post-landing structural condition. The engineers must review inspection evidence and system behavior after each stage before the next envelope expansion is allowed. This precise progression from component extraction to final flight testing represents a supreme act of mechanical stewardship. The proxy rotation, rigid jigs, and new primary load-bearing extrusions each solved a different failure point in the return-to-flight case. The machine that ultimately lifts off the runway will not simply be the same airframe that rolled out of the manufacturing plant in April 1945. It will be the same historic bomber carried through a modern evidentiary rebuild. Yet its historical continuity remains protected, even as damaged material is repaired or replaced where the evidence demands it. The success of the restoration provides a mechanical blueprint for preserving other massive industrial artifacts. The engineering team proved that rigid operational constraints do not have to cancel deep forensic-level rebuilds.